Hey everyone. Today's lesson is pretty important. It's the base, like the beginning of where we're going for the next, couple months. So the ideas I'm going to put out right here are going to be pretty big. So try to follow along with the conceptual side of what's happening. The math itself is not bad. It's the idea behind where we're going today that's really important. So this is called the derivative at a point. That word derivative is going to start popping up pretty much every day. So what is the derivative at a point, or what is the derivative? I'm going to get to that in a second. Let's go back to that example from the average rate of change lesson where I said, okay, if I were to model time and distance, meaning if I wanted to track how far I traveled and then measured it at each time, I could create an in-out table that did that. So I came up with two examples. I came up with one table that looked like this. I think it was this actually. Right? And then this said, okay, at time 0, I started at distance 0. After 1 second, I was at distance of 2 from the beginning. At time 2, I was 4. And I showed you that, at every single moment, I was moving at a rate of 2 per second, 2 meters, whatever, per second. I was traveling at a constant rate of 2 meters per second. That was my rate. Then I came up with the second example that looked a little different, where I had 0, 1, 2, 3, 4, and it looked more like this: 0, 1, 4, 9, 16. And we saw that the rate from here to here was 1, and the rate from here to here was 3, and the rate from here to here was 5, 7. So the rate was always changing. It was never the same thing at any one moment. From 0 to 1, I traveled 1 unit, and from 1 to 4, I traveled 3. So I was never going the same rate. I was speeding up the entire time. So if I asked you for something like my rate at a specific point in time, that's an important question. I want to know how fast was I going at a moment in time. In this first example, it's pretty easy. I was going 2 the entire time. It doesn't matter at time 0, time 1. I was always going 2 feet per second, 2 meters per second. But in this one, I was speeding up. But if I asked you how fast was I going at this moment, I was at position 4. That was my distance. But how fast was I going there? That's the question we want to get at today. That's the idea. So how are we going to do that? Here's the idea. Well, we can model this relationship with a function. So we can call this function f of x, and we can call it x squared. That's, if you didn't guess, that's what the function is. If I plug in 0, I get 0. If I plug in 1, I get 1. 2 squared is 4. 3 squared is 9. 4 squared is 16. So here's my function. And basically, I'm asking this question. What is the, and then I'm going to use this word, instantaneous rate of change. Rate of change at x equals 2. Instantaneous rate of change at x equals 2. Well, that gets really tiring to say instantaneous rate of change. That means derivative. So the derivative is the rate of change at that instant in time at x equals 2, in this case, for some function. So that's going to be a pretty common thing. We're going to find the rate of change at an instant or at a point. So this is the derivative at a point. And we're going to use a tool we've been using so far to kind of come up with a really cool new way of doing this. So let's look at the graph. If you view the graph, I'll just write it down that we're going to go view the graph. And we take a look at the graph of this function, y equals x squared. I'm asking what my speed is right here at 2. What is the change right there? If we go back and look at the original, which was 2x, the linear, the rate of change is the slope, and it's always 2. The slope is always 2 in this problem. But as soon as you make it a function that's always changing, it doesn't really have a slope anymore. But it kind of does. I mean, you can look at it and think about this point right here. It kind of has a slope, and the way you're going to start thinking about it is rather than slope, we're going to start using this word derivative. What happens if you zoom way in? Like you zoom way in on this point. Look what happens. I mean, the line basically becomes straight, and you can almost calculate the slope at this point. So if you look at 2, and you want to find the slope right here, you can almost zoom in so far that you could count it. So if we zoom in and zoom in a little bit more and even more and more, can you kind of approximate the slope? Well, look what it is. It looks like it's up 1, 2, 3, 4 over 1. It looks like the slope is 4 at x equals 2. But is that really what's going on? Well, let's kind of approach it from a different perspective. Here's how we're going to do it. I'm going to come back to this here, and I'm going to kind of draw a little version of the graph. And let's say we have my function, which looked like this. And here was 2 right here. 2, and then this was 4. It's not perfect, but it doesn't need to be, because I'm really going to kind of show you something unique about this. What we just did there with that whole zooming in thing was basically, we can think about the average rate of change, finding the average rate of change in a tiny interval near the point. If we do that, that's a good approximation for the instantaneous rate of change at that point. So if we have our function, and I want to approximate the derivative at x equals 2, I can use AROC to do it. And we can just use a super small interval around 2, maybe 1.99 to 2.01. Because in that moment, if I calculate the average rate of change in that one little instant, well, it's not really an instant, in that tiny interval, that will give me a pretty good approximation of how fast I was going. Think about it. If you're in your car and I clocked your speed at one time, and then like a millisecond later I clocked your speed, you couldn't have changed speed that quickly. There's no way. Both of those speeds are probably going to be pretty close to each other. So same thing here. Using the average rate of change in a tiny interval is probably going to give us a good idea of what the actual instantaneous rate of change was. So to find the AROC, that's what we did the other day. It's f of 2.01 minus f of 1.99 all over 2.01 minus 1.99. And if we pull up our calculator and give this a shot, 2.01 squared minus 1.99 squared divided by 2.01 minus 1.99. My calculator gives up and literally just says 4. It's not exactly 4, it's close enough. So this is kind of a cool strategy for approximating instantaneous rate of change. You can use average rate of change, but there's a better way, and this is where I want to get to. So this is the heart of what we're about to do, and then I'll do 2 examples with you. Can we generalize this idea? Can we generalize this? Okay. The answer is yes. Let's think about it. If we had a function that did this, here's a cool feature I'm going to do, and I want to figure out the instantaneous rate of change at this point right here. So I want to find the slope at this point right here. I want to find the slope at this instant in time. here's what I can do. I can instead think of it this way. Zoom way in on this. I can't zoom in anymore. Lame. I'm going to pick another point right next to it, maybe this point, and call it x. So this value right here is your f of a value. So there's your a, and there's your f of a. That's where I want to find the rate of change or the slope at that point. And then you have this point near it called your x. We're just going to keep it general, and f of x. It could be any point on the curve that's not exactly a. And I'm going to find the AROC between them. So I'm going to say, okay, I'm going to find the AROC between these two generalized points. Well, it would be f of x minus f of a over x minus a. But how do I turn this into the IROC, or the instantaneous rate of change, or the derivative? How can I do that? Well, think about it. The closer these points are together, the better the approximation would be. I really wish they could almost be right on top of each other. I would love it if x and a were as close together as possible. Have we learned about anything in this class this year that allows you to have one value approach another value? Well, hopefully you say yes. And I can change this from the AROC to the IROC, or derivative, by throwing one thing in front of this. I can tell myself that I want x to get close to a as possible without actually equaling a. And this is called the derivative at a point. The derivative at a point. This is going to be our formula that we're going to use for a little bit. The derivative at a point. Okay? Sometimes you'll see this notation, f prime of a. Prime. It's a little apostrophe. So when you see this, this means derivative. Okay, so this is going to be our formula. The conceptual side is a little tricky, but I can show you how to use it, and you should get the same answer that we got of 4. So let's do an example. So use our new formula to find the IROC, or the derivative, at x equals 2. Or find f prime of 2. These are all the same thing. So finding the derivative at 2, finding the average or the instantaneous rate of change at 2, or finding f prime of 2 is all the same, given this function. All right, so the procedure looks like this. We have our formula up there, the IROC, or the derivative at 2. It says to take your function, so the function itself, this port right here, that goes right there, minus what you get when you plug in 2. So we'll do that in a second. Minus f of 2 all over x minus 2, because we're looking for the derivative at 2 in this case. Oh, but then of course I always mess this up. I forgot my limit. The limit as x approaches 2. And now look, we have a little limit problem. Actually, let me rewrite it real fast, and then we can talk about this limit problem we've created. So f prime of 2 equals the limit as x approaches 2 of x squared minus, well, f of 2, when I plug 2 in, I get 4. And now you have a limit problem. And this limit problem should look like one we've kind of seen before. And you can't just plug in 2, you get 0 over 0, which doesn't work. But what you can do is some of our algebraic strategies, like factoring. And you get x plus 2 times x minus 2 all over x minus 2. And lo and behold, cancels out. And we can now substitute in. And we get the answer we assumed we would get. Okay, so that's called finding the instantaneous rate of change, or the derivative at a point. Super important. We're going to be finding instantaneous rate of change all year. We don't have to deal with averages anymore. We can actually find the instantaneous rate of change, which is pretty cool. If you had a graph of a total amount of something, I could calculate the derivative at any instant and tell you how the graph is changing at that instant. Okay, so I'm going to do one more example. If you feel like you got it, you can try the homework. It's all going to fall back on this equation or this formula right here. But let's do one more. Do I have room? Yes. So let's do one more example, and then I'll check it with Desmos to see how we did. So given f of x equals, I'm keeping these very basic so that you guys can try some of the more interesting ones. Let's do the radical function. Let's find the derivative at, same thing, let's find the derivative at 2. Actually, let's do 4, because 4 will be a little bit cleaner answers. So let's find the derivative of 4. Okay, so we set it up. The derivative at 4 is equal to the limit as we approach 4, f of x, which is the function, minus f of a, what we get when we plug the point into the function. So plug that into the function, all over x minus a. F of x minus f of a over x minus a. All right, we can clean up a little bit. And then this should look familiar to you. This looks like another one of the limit problems we've been practicing. Oh my gosh. You can try plugging in. It's not going to work. You're going to have to do some simplifying. And hopefully you recognize that this one, oh my gosh, I can multiply by the conjugate. This time up top. That's why that strategy of the conjugate was so necessary. So in the bottom, we get root x times root, or sorry, in the top, we get root x times root x, which is x. Conjugate middle terms cancel, minus 4, all over. Hey, look at that. We're going to cancel probably with that x minus 4. X minus 4s will cancel. We are left with limit as x approaches 4 of 1 over root x plus 2. And we can plug this in. And it looks like we get an answer of 1/4. So that means at this instant, at 4 in the graph, the IROC, or the slope, or the instantaneous rate of change, or the derivative was this value. I should be able to confirm that. So let's see. Can I confirm that answer? If I come over and graph it, and look at what's happening at 2. So if I zoom way in on 2, or was it, we did 4, sorry. If I zoom way in at 4, do I get a slope that looks like it's 1 over 4? Rise 1, run 4. You're going to have to be the judge. You can just do this all day. I think that's good enough. Ready? How did we do? Let's just go a little bit. There we go. How did we do? Rise is 1, 1, 2, 3, 4. Looks good to me. So yeah, I mean, the derivative is a way to find the exact instantaneous rate of change at a point without having to do Desmos zooming in like crazy. It's a pretty cool, simple algebraic calculation that takes 2 points and basically finds the slope between 2 points that are infinitely close together. That's the derivative, and that's what we're going to be working with for a while. All right, that's it.